Welcome to this presentation. In this presentation, let us have an insight of blood flow measurement. An adequate blood supply is necessary for all organs of the body. In fact, an impaired supply of blood is the cause of various diseases. So, the ability to measure blood flow in the vessel that supplies a particular organ would therefore be of great help in diagnosing such diseases. So, unfortunately, blood flow is a rather elusive variable that cannot be measured easily. And the rate of flow of liquid or gas in a pipe is expressed as the value of the substance that passes through the pipe in a given time. This flow rates are therefore usually expressed in liters per minute or milliliters per minute. Okay, the methods used in industry for flow measurements of other liquids like turbine flow meter and the rotameter are not very suitable for the measurement of blood flow because they require cutting of the blood vessels. So these methods also expose the blood to sharp edges which are conducive to blood clot formation. So practically all flow meters currently used in clinical and research applications are based on some of the principles like electromagnetic induction, ultrasonic transmission or reflection, thermal convection, or radiographic principles, indicator dilution method. So the major two methods are invasive or non-invasive, that is surgical or through the skin. These are the needs of blood flow meter for inspection of block and blood flow and testing artificial blood vessels during organ transplantation and during the fistula creation in dialysis. Some typical values of blood flow are shown here. For aorta of total cross-section area of 3 to 5 centimeters square, the blood velocity will be high, that is 40 centimeter per second. And for capillaries of having 4,500 to 6,000 centimeters squared cross-section area, the blood velocity is 0.03 centimeter per second. And these are the types of blood flow meter: electromagnetic blood flow meter, ultrasonic blood flow meter, NMR blood flow meter, and laser Doppler blood flow meter. Now let us see the electromagnetic blood flow meter. Magnetic blood flow meter are based on the principle of magnetic induction. When an electrical conductor is moved in a magnetic field, a voltage is induced in the conductor proportional to the velocity of the motion. The same principle applies here also. When the moving conductor is not a wire but rather a column of conducting fluid that flows through a tube located in the magnetic field. And this figure shows how this principle is used in magnetic blood flow meter. A permanent magnet or electromagnet positioned around the blood vessel generates a magnetic field perpendicular to the direction of blood flow. The voltage induced in the moving blood column is measured with the stationary electrodes located on opposite sides of the blood vessels and perpendicular to the direction of magnetic field. And the most commonly used types of implantable magnetic blood flow probes will have a slip-on or C-type applied by squeezing an excessive blood vessel together and slipping it through the slot of the probe. And in some transducers, models of the slot is then closed by inserting the keystone-shaped segment of plastic, and the contact is provided by two slightly protruding platinum discs that touch the wall of the blood vessel. So for proper operation, the orifice of the probe must fit tightly around the vessel. For this reason, probes of this type are manufactured in sets with diameters increasing in steps of 0.5 or 1 mm from about 2 to 20 mm. The probes can be implemented for chronic use. And in contrast, a long handle for use during surgery can also be used. And as we can see, the induced EMF in an electromagnetic blood flow meter is given by E is equal to integral or UBdl. where u is the instantaneous velocity of blood in meter per second, and b is the magnetic flux density, and L is the length between the electrodes. The magnetic blood flow transducers are also manufactured as catheter tip transducers. For this type, the normal transducer design is essentially turned inside out, and with the electromagnet being located inside the catheter, which has the electrodes at the outside. The catheter transducers cannot be calibrated in flow units, however, because the cross-section of the blood vessel at the place of the measurement is not defined. And the output voltage of the magnetic blood flow transducer is very small. It will be typically in the order of few microvolts. In early blood flow meters, a constant magnetic field was used, which caused difficulties with the electrode polarization and amplifier drift. To overcome these problems, all contemporary magnetic blood flow meters use electromagnets that are driven by alternating currents. So doing this, and however, creates another problem. The change of magnetic field causes the transducer to act like a transformer and induces error voltages that often exceed the signal levels by several orders of magnitude. Thus, for recovering the signal in the presence of the error voltage, amplifiers with a large dynamic range and phase sensitive or gated detectors have to be used. To minimize this problem, several different waveforms have been advocated for the magnet current, and with the sinusoidal magnet current, the induced voltage is also sinusoidal but is 90-degree out of phase with the flow signal. With suitable circuits similar to a bridge, the induced voltage can be partially balanced out. Right, and with the magnet current in the form of square wave, the induced voltage should be zero once the spikes from the polarity reversal have passed. In practice, however, these spikes are often of extremely high amplitude, and the circuitry response tends to extend their effect. A compromise is the use of a magnet current having a trapezoidal waveform. So none of the three waveforms used seems to be demonstrated a definite superiority. And the oscillator, which drives the magnet and provides a control signal for the gate, operates at a frequency between 60 to 400 Hz. The use of the gated detector makes the polarity, the output of the output signal, reverse when the flow of the direction reverses. And the frequency response of this type of system is usually high enough to allow the recording of the flow pulses. And the second category is ultrasonic blood flow meter. In the ultrasonic blood flow meter, a beam of ultrasonic energy is used to measure the velocity of flowing blood. This can be done in two different ways. In transit time ultrasonic flow meter, a pulsed beam is directed through the blood vessel at a shallow angle, and its transit time is then measured. When the blood flows in the direction of the energy transmitter, the transit time is shortened. So if it flows in the opposite direction, the transit time is lengthened. Most common or ultrasonic flow meters are based on some Doppler principle also, and the figure here shows the ultrasonic blood flow meter. So here the transmitter sends the ultrasonic signal, which gets reflected by the red blood cells, and then the signal is received by the receiver. And the second category is Doppler shift blood flow meter. Here an oscillator operating at a frequency of several megahertz excites a piezoelectric transducer, and this transducer is coupled to the wall of the exposed blood vessel and sends an ultrasonic beam with a frequency of F into the flowing blood. A small part of the transmitted energy is scattered back and is received by a second transducer arranged opposite the first one. Because the scattering occurs mainly as a result of the signal, moving blood vessel signals, the reflected signal has a different frequency due to the Doppler effect. So this difference in frequency, that is F plus Fd or F minus Fd, depending upon the direction of flow, the frequency will change, and the Doppler component AFD is directly proportional to the velocity of flowing blood. A fraction of the transmitted ultrasonic energy reaches the second transducer directly, with the frequency being unchanged. After amplification of the composite signal, the Doppler frequency can be obtained at the output of the detector as a difference between the direct and the scattered signal components. So the Doppler shift blood flow meter can measure three informations, that is presence or absence of flow, direction of blood flow, or velocity of blood flow. So suppose if the transmitted frequency is Ft and the received frequency is Fr, the frequency shift detected will depend upon two factors, the magnitude and direction of blood flow. So the figure shows the principle of Doppler shift blood flow meter. So the Doppler frequency shift, that is the difference between the Ft and Fr, is calculated by subtracting the transmitted signal Ft from the received signal Fr. Thank you.